So this is lab 5. So the purpose of this lab is to compare the predicted motion and the observed motion of a Slinky being dropped from rest. I used a model from Tracker to see how different forces affect a Slinky's motion and position after being dropped from static equilibrium. Using closed script, this lab uses fundamental physics principles to model these motions, and these principles include, in the computational model, the position update formula and velocity update formula work. And they're of importance as they allow us to predict what the change in position over time and velocity are. Next, Newton's second law explains how the acceleration of an object is proportional to the mass of the object and the net force acting on it. Additionally, the energy principle, which states that the change in mechanical energy of a system is equal to the work done by the surroundings, is used, and you can also see the different formulas for different types of energy and work broken down. I also use different formulas for the force of drag, the force of spring, and the force of gravitation in the GlowScript code. So in the experimental model, the system is the mass of the Slinky, while the surroundings includes the Earth and everything else. The calibration length used in Tracker was a distance of 1.76 meters, and as for the initial conditions, the object had a mass of 0.206 kilograms, and it was released from time 0 seconds. In the experimental model, we assume that in placing the tracker points, they're accurate per delta t. We also assume that the perspective of the video doesn't affect the accuracy of how the axes are lined up, since there's only the x and y axis. So here you can see how the video was analyzed in Tracker. So I had the positive x-axis pointing to the right and the positive y-axis pointing upwards. I also made the center of origin to be the bottom of the Slinky. So the computational model uses Python and GlowScript to create a theoretical model of the Slinky, with, again, the system being the Slinky and the surroundings as everything else. So I found these initial conditions using the tracker data, where the initial position was 0, negative 0.0025, 0 meters, and the ball was released from rest, or the initial velocity was 0. So I have the acceleration due to gravity in Earth and the drag force here. I calculated this through trial and error by trying to make sure that the final position in the computational data was the same as the final position in the experimental data. So here are the two while loops I used. So the first one is accounting for the time it takes for the top of the Slinky to reach the bottom while the bottom remains stationary. And the second while loop is for when the bottom of the Slinky falls as well. So I used both the velocity and position update formula under both these while loops, and also calculated the net force using falling forces. Looking at the results of the lab, so the observed and predicted drag data differ a lot, and this may be due to human error when using Tracker, as mentioned before for the observed data. Additionally, it may be due to unaccounted forces in the computational model. So one way to make the data more accurate could be to track the motion of both the bottom and the top of the Slinky. So to further think about physics concepts in this lab, we can look at the discussion questions. So yes, the bottom of the Slinky does remain stationary until the top of the Slinky reaches it. So essentially, the bottom of the Slinky stays stationary because the tension force and gravity force act in equilibrium. So if you draw out a free body diagram, tension will go up while gravity goes down. So they sort of cancel each other out. But as the drag force increases, the bottom of the Slinky begins to fall as well. And just to conclude a bit, so there are different sources of error, as mentioned before, and it's also important to note that friction and drag were not fully represented, as the video couldn't fully capture them, and this could have